Do you have any kind of break between classes?
Before the SAT.
Yep.
During group 2.
I'm free, what time is it now, 11? I'm free from 2 o'clock. Any time after 2 o'clock. No, but even like a few minutes between classes. Yeah, run to the teacher's room. I can show you.
ESAP at 2 o'clock.
Just before ESAP, maybe. Where's the SAP? In this building or?
8.
Okay. I'm sure Stephen B won't mind if you're a couple of minutes late. Okay, so we'll start now the next topic. Okay, so what we're going to look at, there's 6 parts of the course, so we're on part 4, which is the materials. And in particular, in materials, we're going to look at something called specific, there we go, specific heat capacity. Now, you know that whenever you make tea, it takes a few minutes for the water to heat up. Yeah? Now, how many people here have a cooker at home? You know, like the top where you can put the pot. Yeah? So which gets hotter quicker? The top of the cooker or the water in the kettle? Which do you think gets hotter? Top of the cooker gets very hot very quick, doesn't it? Yeah. Whereas the water, if you boil the kettle, takes a few minutes. So this is our idea. Our idea is different things get hot at different speeds, at different times. So can you give me some materials that get very hot very quickly? And metal would get hot quickly? What else? Silver, yeah. Copper, yeah. Now the opposite, things that take a long time to get hot. Water, wood, plastic. So if you think about chemistry maybe, is there any way to describe the difference between metal, silver, copper, this stuff, and then plastic, wood, water? Yeah, we'll just keep the term simpler, but you have the right idea. Yeah, I was thinking the copper, silver, that's a conductor. You know this word from chemistry? And then what about plastic, wood, they're insulators. So in fact we can see a relationship. When something is a conductor, it can get hotter quicker. And if it's an insulator, it takes longer to get hotter. So we need some way to measure this, and that's what specific heat capacity is. So I'll give you the definition here, which I'm sure you probably know. I'll just write SHC for short. The specific heat capacity of a material is the amount of energy required to raise the temperature of 1 kilogram of the material. Sorry, this sentence is ridiculously bad. 1 kilogram of the material by 1 Kelvin or 1 Celsius. And yes, you can use grams if you want. Just be careful which one you're using in the exam. So I'll give you a little picture here so you can try and picture it. If you have 1 kilogram of water Now maybe somebody knows this already, and you have here it's at temperature T, Kelvin, and you would like it to increase to temperature T plus 1 Kelvin. Does anybody know how much energy you need to put inside of it to cause it to do this? No, the number. Yes? Yeah, in fact you need about 4,200 joules for water to raise 1 kilogram by 1 degree. That is the specific heat capacity, yeah. Now that is very large, and again to show you how large it is, we'll have a look at an example from home. Can I scroll down? Yeah. So, let's take an example, e.g., our first example. Actually, before the first example, I'll just give you the formula. So, the formula is, if you would like to know how much energy you need to increase the temperature, you just multiply the mass by the specific heat capacity, that's the C. Now that's a big C, okay? Not a small c, so I'll write bigger. By how much temperature change you want, the change in temperature. So this is the formula, and this really is the only formula for today. We can see what the units are for the C.
What's Q?
Q is heat energy. I'll write these in. This is how much heat you need, heat energy in joules. This is kilograms. This is Kelvin or Celsius, doesn't matter. I prefer Kelvin. And then C, we can see what the unit is, and it's joules per kilogram Kelvin. Okay? So let's have a look at our first example. How much energy do I use to make tea? Now my example is a little bit silly because I don't give you any numbers in it. So we'll work out the numbers ourselves. Yeah? Okay, if I go down. So in the question, they'll give you the numbers, but just as interest, let's try and do the numbers ourselves, okay? So if you want to make tea, how much water do you think you have? You make some tea. How much water? Give me its mass, what do you think? 2 kg?
No.
That's an awful lot of water. T for 1.
300 minutes.
Now give me in grams or kilograms. Huh?
500 grams.
Yeah, about 500 would make 1 cup of tea. So if you wanted to make 1 and a bit or maybe 2, we'll say 1 kilogram to make it easy, okay? So we have 1 kilogram. What temperature would the water be at when you get the water from the tap? What's its temperature?
16 degrees.
Huh?
15.
I don't know. Well, it depends if you have hot water, but if you're using cold water, I think it's colder than this. I think more like 12 or something. I don't know what your home is like, but the cold water in my home is very cold. Yeah. So we'll say maybe 10 degrees. Now what temperature do you want your water to go to?
45.
Oh, not 45, for tea. 100. 100. You want it to go to 100 degrees. Yeah? Okay. So let's write down our information. What's the N? 1. What's the change in the temperature?
90.
90. And what's the specific heat capacity of water? I gave it to you earlier. It's about 4,200. So, how much energy do I need? Well, the formula is mc delta T equals 1 multiply 4,200 multiply 90. What's that, please?
It doesn't matter if you use Kelvin or
Does not.
3.78 times 10 to the power of 5.
3.78
78
times
10 to the power of 5.
10 to the 5 joules. Yeah? Is that right?
Yeah.
Or, to put it another way, 378 kilojoules. Now look, what you must appreciate is that is a really big amount of energy. To make 1 cup of tea or 1 mug of tea, you use 378 kilojoules. Kilojoules. So, what I'm trying to get you to learn as well is to heat water uses a lot of energy. In fact, in your home, heating water is the most expensive thing you can do. If you want to heat water to take a shower, take a bath, make some tea, make some supper, this uses the most energy. Okay, so heating water, a lot of energy. This is why they say when you make tea, only use as much water as you need. Because if you boil water and don't use it, you're wasting a lot of energy. Okay, so it's good to know this stuff. Okay, let's have a look at another example. I'll give you another interesting example which I like. So the tea one I like. Can I go down? Yeah? Okay, another example. Okay. Now, for this example, what we have here is a waterfall. And just to make this example a little bit easier to do, I'll just say up here, we'll say the speed of the water is quite slow. So it's not really a waterfall, maybe it's more like just like a little stream or something. But we'll just say it's roughly 0. And down here maybe some kind of pond, the water collects. And we'll say here it's about 0 as well. Now we know it's not 0, but just for my example we'll say it's about 0.
Speed of the water?
Yeah, the speed of the water, yeah. Now of course it can't be because it's falling. It's moving. But we'll just say for this to make it simple, it's 0. Okay? Let me just check my battery. Yeah, it's okay. Right. Now, when you look, and let's say this here is 100 meters. Okay, so let's look at 1 kilogram of the water. There's 1 kilogram there. It'll fall down and hit the pool down here. 1 kilogram. What is the energy at the top? What type of energy does this have at the top?
Yeah, that's right.
It's just potential energy, isn't it?
Yeah.
This piece here of the water. Which is what's the formula? mgh. So in this example, if m is 1, h is 100, and g is 9.81, this will be 981 joules. Now down below, what type of energy does this have down below? Does it have potential? No. Does it have kinetic? No. This energy has turned into heat. The water down below is warmer than the water at the top. So this is true. When you have a waterfall, the water at the bottom of the waterfall is warmer than the water at the top. So, does it have kinetic? No. Potential? No. What does it have? It just has
So
heat. Yep.
It goes from potential to kinetic to heat, right? Because
Yeah, I suppose so. If you were tracking it, potential, it's falling, it's kinetic, but then when it hits the bottom, the kinetic turns into heat. So we can skip the falling part. Okay, so let's work out how much warmer this water is. So we use our formula, mc delta T. That should equal 981, shouldn't it? Because the energy at the top equals the energy at the bottom. What's the M? 1. What's the C? 4,200. So if you type that in, you should get about 0.25. Two, three, yeah?
2, 3, 4.
Okay, 2, 3, 4. Yeah.
Go up, right?
Okay. To where? Here?
Oh, okay.
Now that's not much, but it's enough that you can measure it. Yeah? I want to give you one to try. Can I scroll down? Yeah, okay. So here's my example. I want you to try and then I'll do it. So here we are. Here is some copper. And here we'll say is 150 meters. And we'll say it's 2 kilograms of copper. And the person comes along, gives it a little push, and it falls. It hits the ground with a speed, but then it kind of wobbles and comes to rest. Okay. So we'll just say when the boy just gives it a little push, just to knock it over the wall, just a little push. So we can say approximately 0 meters per second. Okay, so my question is, how much warmer is the copper? And what I haven't told you yet is the specific heat capacity of copper. So do we think this is bigger or smaller than water? Is it a bigger or smaller number?
Smaller.
It's smaller because it needs less energy to get hotter. Is it much smaller? Yes, it's about 10 times smaller. It's 400 joules per kilogram Kelvin. So using this number here, and then here's the mass, here's the kinetic energy at the start, here's the distance. There's enough information there so that you can tell me how much hotter this piece of copper is. Actually, I think that's a bit too big. We don't want to kill anyone. Let's make it 0.02. Okay, try that for a minute, then I'll do it on the board. Does anyone have an answer? Yes? Okay. 3.6.
6,700.
Yeah, so that's a lot warmer, isn't it? Like you can feel it warmer. So just to do it really quick here, the energy at the start is just potential energy, which is, what is it? M, G, and what's the H? 150, wasn't it? So what does this work out as?
294.3.
Okay. And all of this energy at the end gets turned into heat, which is mc delta T. So you have, therefore, mc delta T equals 294.3 joules. So then delta T would equal 294.3 over 0.2 by 400, which is 3.67 Kelvin. Yeah. So nearly 4 degrees increase in temperature when you drop the copper off the building. Yeah. You could definitely feel that. Okay, let me give you another example, a little bit more difficult now. And again, well, no, maybe do I have time to let you try it? I'll let you try it first. Maybe some people can get it. Then I'll do it. Okay. So here is, let's say, 500 grams of water at, I don't know, 50 degrees. And then here, let's say this is oil. Let's say it's, 400 grams of oil. And let's say this one is at, I don't know, 70 degrees, something like that. Yeah. So what I do is I mix the two together. Put them in one container. My question is, what is the temperature of this mixture? Now I'll give you a little hint. So just before you write it down. Yes? Can you look up just to get the hint, okay? Because it's a little bit more difficult than the other two. So what we do, there's the mixture. My hint is, colour this in red, colour this in blue, or whatever, and in the mixture, don't separate them. In the diagram. Now, when you think about it, what happens when you mix oil and water together? They don't really mix, do they? The oil sits on top of the water. But that's good, because it helps you to picture the best way to do this. Even if they do mix together, in your picture, draw them like one sits on top of the other. And the reason for doing that is it helps you to keep track of what's happening. Which of the two materials is hotter, the water or the oil? The oil. So what's going to happen here is some of the heat from the water will go into the oil. And they're both, you know what, I'll do it, okay, because I think, sorry, what did I say? From the oil to the water, sorry, yeah. You know what, I'll do it, because I just realised it's a little bit too difficult if you haven't seen it before. So I'll do this one here, okay? Right, so if we look here, this temperature, I'll call it X. I don't know what it is, I'd like to know it. Okay. Oh, I haven't told you the specific heat capacities. Let's say specific heat capacity for water, that's 4,200 joules per kilogram Kelvin. And then for oil, let's say, I want to make it about the same, so I'm sure this is too big, but I'll just say, I don't know, 3,000, but I'm sure that's way too big. 3,000 joules per kilogram Kelvin. Okay. Now this is what we do. I'll put an equal sign here to start. The energy, well, I think this is important enough that I need to be standing. The water is hot, but the oil is hotter. So in our head we picture the water gets warmer, and then what happens to the oil? It gets cooler. So when you look at this picture, when you put the water in the middle, it gains or loses heat energy? Gains. And when you put the oil in as well, what happens to the oil? It loses. And that's the key. The energy the water gets is equal to the energy the oil loses to keep everything balanced. Okay? So, how much energy does the water get? Well, what's the formula for that? I'm going to have to plug this in. For the water, it's MW, C for water. What? Leave me alone. Delta T for water. That should equal how much energy the oil lost, which is the same formula. M for oil, C for oil, delta T for oil. Let me just plug this in. What's the M for water, please? 0.5. And what's the C? 4200. What's the delta X? Well, no, it's the change. So does it get hotter or colder? It gets hotter. It's going to be X minus 50. No minus.
X minus 50.
Because it's the change. Remember, delta T is the change in the temperature. How much you gain or lose. Yeah? Good. Okay. Mass for the oil? 0.4. Specific heat capacity? 3000. And then the temperature here? Well, again, I'll just do the same thing, except this time I'll just do it 70 minus X. And the reason for doing that is to make sure I get positive and positive here on both sides, just so I don't have any sign problems.
So if you make this one positive, same thing.
If I made this one positive?
That's not positive.
Sorry, what I mean to say is, you might be saying, why don't I do X minus 70? I know that number would be negative. X, we picture X being somewhere between 50 and 70. So I just want to make sure both of these are positive for the delta T. Now sometimes you need to be careful and use the minus, okay? For this problem I don't need to worry about minus. I can do it fine if I just make everything positive. If I basically say the gain here equals the loss here, make them both positive. But when they get more complicated, it's not as easy as this. But anyways, you realize now that you pretty much have it done, don't you? Because it's just an equation for X to solve. So can you tell me please, well actually I don't need it here, this is 2100X minus, what's this, 25? No, times 4200. 25 times 4,
10,500.
what is it?
10,500.
10,500, okay. Equals, now,
84,000.
84,000
minus
No,
1,400.
8,400
Yeah.
minus,
It's 84,000.
oh hang on please,
What?
just,
It's 84,000.
guys,
0.45.
this one here, 0.4 times 300 times 70, what is it?
Yeah, it's 84,000.
Times,
8,400.
ah, I see we're back into our problems we had in semester 1.
It's 84,000.
Spanish, I'll come down and hit you if it's, 8,400. This is what you were saying, yes?
You said 84,000.
Oh, that's
Yeah.
capacity is 300. Okay, I mean, it's 3,000.
Oh, no, thank you, that's my mistake. It should be 3,000.
Yeah, then 84,000.
Alright, my bad. 84,000. Okay, next. Alright, so what's the last one here?
1,200.
4,000.
1,200.
1,200.
Okay. So we get, let's see, 3,300x equals 94,500? No.
Yes, it is.
Yes?
Yes.
Did I add those two numbers correctly?
Yes.
This one plus this one? Yes?
Yes.
Okay, so
That one, 105,000.
000, okay. So what do I get here now?
No?
No, it's not. It's a bit much bigger. 189,000, yeah? Okay. So finally, divide that by 3,300, and you get for x, should be somewhere between 50 and 70, I sure hope.
57.3.
57.3 degrees.
57.3.
So that is the temperature of the mixture of the oil and the water.
Yeah.
Okay.
So the water gets 7 degrees.
Yes, the water increases to 57 and the oil decreases to 57. The biggest mistake here is with signs. You can be very careful about that. Now I won't do it, but I'll just outline a more complicated one you can get in the exam. Okay. So for example, sometimes you get this. Sorry, that's a in case you can't tell, that's a cup. I'll put a handle on it. There we go. The cup. Now, we would say something like, okay, this cup is copper. Maybe it's 100 grams, and maybe it's at 20 Celsius. And then what I do is I put in some hot water. Let's say this water here is 300 grams. And then let's say it's 80 Celsius, yes? And then I put in some milk. You can guess what I'm making here, can't you? Okay, yes. I put in some milk, and let's say the milk is probably going to be about like, let's say 2,000, let's say 20 grams, and its temperature, it's going to be pretty cold, we'll say it's 2 degrees. And the specific heat capacity of water, that's 4,200. Do you remember what copper was? 400. And we'll say for milk, it's 2,000, we'll say. Just make it up. So then my question is, what is the temperature of the cup, the milk and the water? They'll all be the same temperature at the end when you mix everything together. Now, you have to wait a minute or two for it all to settle down, but they'll all be the same temperature at the end. Now you might say, well, wouldn't that burn my hands? And you say, yes, that would burn your hands. That's why you don't use copper cups for your tea. You use plastic cups, because they're bad conductors, okay? So don't use copper cups for your tea. Yes, it's quite bad. So here, I won't do it, but I just want to write down the equation to solve. So tell me, the copper here, does it gain or lose energy? Gains. The water, gains or loses? Loses. And the milk, gain or lose? Gains. So I just want to write down what the formula would be. So the formula would be, well, yes, but if I just write it all out as one, I could say the gain in the copper plus the gain in the milk equals the loss in the, why are you distracting me? The loss in the water. And just make sure that all of these numbers are positive numbers, okay? Make sure they're all positive. So, just one more line and then I'll stop. You have the mass of the copper, yes? Then you have the specific heat capacity of the copper, and then what would be the change in the temperature? Well, would it be X?
X minus 20.
X minus, what's the copper? 20, isn't it?
Yes.
Okay, and then for the milk, it's the mass of the milk, the capacity of the milk, and then what would be for the formula? It would be X minus, what did I say the milk was? Like 2?
Minus 20.
2 for the milk. Milk is quite cold. And then for the water, it's mass of the water, specific heat capacity of the water, and the temperature would be 80 minus X. Yeah, that's the change in the water temperature. How many things in that formula do you not know? Just the X, isn't it? Do you know the masses? Yes, it's given. Do you know the specific heat capacities? It's given. Can you solve this for X? No problem. It's just a linear equation, isn't it? So the key thing, the key thing here is, wouldn't be so familiar, this question is usually like in the exam a 4-mark question, 4 or 5. The key thing is, once you write this equation down, you got it. You just go down to solve it, okay? Now I don't want you to solve it now, I want you to solve it for homework. And then I'll give you some questions here. Now I didn't give you the answers, and the reason I didn't give you the answers is because we're going to do these in the next class. Alright? So you'll actually see the answers. So these are just the questions. It's 2 pages each. Two pages each. Why don't you have answers? What did I say? Because I'll do it in the next class. So there are in total 6 questions there. I'd like you to start them now, and I want you to finish them for homework. You don't have to do this one right now, you can do this one later at home. Or you can finish it now, I don't mind. But most important for me is, I want these 6 questions done for the next class, which is when? Tomorrow?
Yeah.
There? Tomorrow? Okay. So work on them now for a minute, please.